Alexis, and she'll be telling us about different compilation methods between Racket and Haskell.
All right. So this is my sort of least favorite type of talk to give, or at least to hear, which is tell everybody else something that they should do type of talk, rather than presenting something that I have done. But as some of you may be aware, I have spent a lot of time in both the Haskell and the Racket communities, and I feel like there's an unfortunate dearth of cross-pollination. So, but in order to sort of motivate that, I actually want to start by talking about some Haskell stuff. So, in particular, as sort of people who work on GHC, we often think of GHC as this, center of the universe, and it's all that exists. But of course, as a Haskell programmer, you spend a lot of time working with and interacting with lots and lots and lots of other tools that we don't really think of as being part of sort of GHC's responsibility. And so that could be anything from Cabal, the build tool, Haddock documentation, Hoogle for searching that documentation, HLS for developing Haskell programs, and various profiling and debugging tools. And a lot of these tools, frustratingly, don't always work together nearly as much as we would like. And in fact, this is something that I think has come up a little bit here and there in some of the discussions already. And in particular, I want to give an example, just a concrete example of something that I found personally very frustrating, and that's with respect to Hoogle. So Hoogle is wonderful. I think that when I work in an ecosystem that doesn't have something like it, it's very frustrating. But there is one problem with using if you go to hoogle.haskell.org, and that's this little drop-down box in the corner, which specifies that the set of packages that you're searching are the set of packages and their versions that are currently on Stackage. Now, that's often very useful, but if I'm actively developing Haskell code, this set of packages doesn't necessarily match the set of packages that I'm using, because they might have different versions, or there might be packages that aren't on Stackage. So what if my local packages are different? Well, this shouldn't be a big challenge, right? We should be able to just open up our terminal, install Hoogle, and generate our own Hoogle database. But if we do this and we look at sort of the set of options that Hoogle provides, there seems to be a fairly promising option in this list, which is this local item here. That sounds like what we want. So let's run Hoogle generate with that local flag, and then we go back and run the little server, and it says set installed, but I don't have my local packages there. Why? What went wrong? And remarkably, this is actually very difficult to fix currently. If anybody has a better solution, legitimately tell me about it, because I would really appreciate it. Because if you, basically the issue here is that while obviously Hoogle is involved, so is Cabal, because Cabal is managing the set of packages that are currently installed in the current project. It knows what those are, where they live, and Hoogle does not know about that. So if you actually want to do this properly, you have to pass as the argument to this local flag the path to not just where the packages live, but the actual directory where the HTML generated documentation shows up. So the question is, how do you get that list of directories? It's actually pretty hard. And in fact, the only way that I've really found to reliably do it is to run cabal build with this write GHC environment files flag. And this flag will generate a big long file that looks like this. And if you can't read it, it's not too big a deal. It basically just says, here's where the package databases are, here's the package IDs. And so this at least tells me what all the packages are in my current project, and it just ends up in this file, which really I think is mostly just intended to be consumed by GHCi, for example, to configure the interactive environment. But this does at least tell me what the packages are, but it doesn't on its own tell me where they live, and in particular where that how.html directory is. So the only way that I managed to actually turn this information into what I wanted was to write a 50-line Racket script, and obviously it doesn't have to be Racket, but that's what I did. And obviously the code is very tiny here. I'm not even going to talk about what it does. It's not interesting. It calls GHC, PKG, and calls dump, and that information is spat out in a format that I then have to parse, and it's miserable. This is terrible. I hate it. And it's remarkably common when I use Haskell tools that they simply do not seem to know of each other's existence. They seem to be totally unrelated from each other. And we kind of have to ask ourselves, why are things like this? Because other ecosystems other ecosystems do have problems like this, but not universally. Some of them are at least somewhat better. So who are those people that manage to do a little bit better, and what are they doing that we are not doing? So obviously the example ecosystem I'm going to be giving here is Racket, and there are many other ecosystems that I could be talking about. Java is an ecosystem that has really, really wonderful tooling, but Java is also an ecosystem that's very different from the Haskell ecosystem because obviously there's an enormous amount of money in it, but Racket is very, very small. It's actually significantly smaller than the Haskell community. There's a lot less money in it. There's almost no money in it, and yet they have managed to produce a set of tools that work very, very well. So, one reason this might be the case is that perhaps Racket does in fact just kind of bake all that stuff in to the core. But this is not the case. Racket also has its own build tool, its own documentation tool, its own IDE, its own debugging tools, and its own profiling tools. And while there are, to some extent, some hooks somewhere to sort of provide a little bit of functionality to help these things get started, for the most part, they really do live independently. And in fact, they almost all live in their own Git repositories. So one possible explanation is maybe that the Racket people just care about this a lot more, right? They've chosen to focus their efforts on developing these tools. And I think this is sort of the common intuitive explanation as to why they managed to do this so well. Racket people care about tooling. And I think that's true to some extent, right? It's certainly the case that due to its sort of history as an educational project, there was a lot of initial work in this direction. But I don't think it's the full explanation. And so this finally brings me to the thesis of this talk, which has 3 parts. The first is that Racket has produced exceptionally powerful and reliable tooling for such a tiny community. 2, the quality of this tooling is not just social. There is a significant technical factor, and that those technical decisions are things that we could actually also incorporate, at least in some capacity, maybe adapted into the way that we architect these tools in Haskell. So the actual payload here is actually not going to be very complicated, but it requires understanding the difference between how GHC and Racket sort of see the world. So in GHC's world, basically we have in order to compile something, we give it some set of modules, we give it some input file, we run it, and we get some files out. This is sort of the way that we see GHC. Now, obviously, there are some variations in this. GHC has a make mode, but for the most part, GHC is a traditional batch mode compiler. You feed it files in, you get files out, you link them together, and you get an executable. This is very, very, very different from the way that Racket sees the world. So in the Racket world, the compiler is sort of hidden, and Racket itself is primarily a runtime. And then on top of that are built a loader, linker, expander, compiler, and these things aren't really directly interacted with by the user, maybe to some small degree. And then on top of that, core libraries and core tools. So the way that people actually interact with this is that Racket is essentially a programming environment or a runtime environment in the style of a Lisp machine. And of course, it's not actually hardware, and it's not even really an operating system. But there's a lot of similarities here in that Racket is sort of the system that you run. Now, if you basically provide, this sort of looks like running an interpreter, where when you want to run a Racket program, you provide it a source file. And basically what happens internally is it's basically the same as spawning a REPL and then, executing some command in the machine to load a module. And this looks a lot like, okay, it's an interpreter. And interpreters have a lot of real downsides. But I think it's worth emphasizing that Racket is a fully natively compiled programming language. In fact, as of a few years ago, it doesn't even use JIT compilation. The compiler, this is running the compiler. So in a sense, you can invoke the compiler at runtime, but every time you load some code, any code, it gets compiled to native code, and then that code gets executed, and there's no additional compilation after that fact.
Alexis, is it compiled at that moment? Or the files lying around?
That's a good question. So if you don't explicitly ask for it to be compiled ahead of time, then it does get compiled at that moment. But you can explicitly ask for it to be compiled ahead of time, and then those it doesn't write like operating system standard .o files, but it does write native code blobs to disk, and then those native code blobs get loaded in much the same way that loading a .o file or some library would work in GHCi. Does that answer your question?
So if your little source file depends on 100,000 lines of imported libraries and so forth,
yes,
they all get compiled?
They could. Of course, in practice, there's some Racket tools so that when you like install a package, it will compile all of the modules in it and things like that. So, but I think the key point here is that for the most part, that is transparent to the user. They don't really think about invoking the compiler. They don't think of it as, it's sort of like if you run this, it's a way to say, I want my load times to be faster the next time I run my program. But then if you change something, it's basically just a cache. If you change something, then it will invalidate that and it will recompile it on demand. So it's just sort of a way of saying, do this ahead of time so that I don't have to do it later. It's an optimization. It's not like a core operation. That makes sense? All right. So I think to many people, this model seems remarkably impoverished. This doesn't seem good. This seems like a downside because we like being able to take our input program and turn it into a output program, and we don't want to ship the compiler with our program. It's a very reasonable thing to want to do. And indeed, I actually think that there are some significant downsides to this specific implementation strategy. But I also think that it's a little bit, there are two very different ways of looking at the world, and that way also sort of ignores some of the things that are very interesting. So in Haskell, we think of a REPL as basically an interactive tool for exploratory development, right? That's what GHCi is. And in Racket and in Lisp, that's also true to some degree. But there's another perspective, which is that, okay, actually, I already said that. But in Racket, the REPL is effectively a shell by which you interact with this Lisp machine environment, right? So there's a bunch of little commands like loading something, compiling it, evaluating it. And the REPL is really just sort of the way that you drive the system. And so in this sense, this is an implementation strategy for achieving a compilation server, right? There's a bunch of states that's part of the machine, and you have a dialogue with that machine where you sort of submit compilation requests or load requests, and that state ends up in the current state of the machine. So just to give like a little example of this, we can import, or just to give an example of having such a dialogue, we can import this library here, and then I can call this package directory function, and it will just tell me what the path to this slideshow library, which is the library that I actually use to generate these slides, and it'll just tell me. And that's something that's very, very nice because we're just able to provide a function for doing that. We don't have to worry about, well, okay, which executable does it live in? What command do you pass? There's just a library, and this is just one of many, many functions. And we can also do more interesting things as well. So we can say, here's this syntax transformer module, and I want to know what it provides. So I can just call this module to exports function, and I can pass it this module name, and it tells me. And I'm not going to go into the details of what exactly the representation means or what these things are, but it's very easy to do. And of course, this is similar to what we can already do in GHCi, in the sense that GHCi also has commands for sort of, you have :I, :info, and that can tell you things about the structure of a module. But this is, again, these are Racket functions, right? They're not a fixed set of commands, and technically you can expand the set, you can extend the set of GHCi commands, but it's not designed to do that, and I think almost nobody does that. In fact, I would be amazed if a single person in this room had actually done that. Wow, 2, 3, very impressive. So you can abstract over these things. You can assemble them together into much more elaborate abstractions, including in libraries, which is often done. And this means that you don't have to write a bunch of shellcode to glue everything together, which is very, very nice. So here's another example. So this is sort of similar to the Hugel example I was talking earlier. So I'm just going to import some libraries. Scribble is the sort of Racket documentation tool. And I'm going to call this load collections cross-references function. And then I can do a couple things, and I can say, give me, by calling xref index, then I can say, give me a list of all the things that are indexed in this documentation. Let's just take the first 3 of them, pull out the entry tag, and here's just the first 3 things, returned in a sort of arbitrary order. Just first 3 things that happen to be in my entire set of installed documentation. And what's remarkable about this is that, I guess 2 things. One, I did not configure anything, right? I didn't specify search paths. I didn't specify anything along those lines. It just kind of magically knows how to do this. And second of all, the output that I get here is these libraries are not defined in the core. These libraries, these setup, crossref, scribble, crossref, are derived abstractions that exist in libraries that I just happen to have installed, packages that I happen to have installed. And they're built in terms of those sort of more core functions. But because of the fact that they're just functions, they can, again, be assembled to create these more interesting things. So here's one final example. This is the macro stepper. Racket has macros. And so the macro stepper is an interactive tool that you can use to step through macros, not really particularly shocking. And normally you access it through this sort of GUI interface that lives in Dr. Racket, the sort of Racket provided IDE. But what if you don't want to use Dr. Racket and you want to use Emacs? Macro stepper works fine there as well. And the reason for that is that, again, you can just import the macro stepper, and there's this particular API for it. Then you can make some call and you can invoke it, and then you get a sequence of steps in much the same way, but in a textual format or in a structural format. And again, this is very, very nice because while absolutely it's the case that sure, there's sort of standalone tools, those tend to be very thin wrappers around these APIs. And these APIs are public APIs, right? They're sort of intended to be consumed. And so there's really the strong culture of you don't just build an executable, you build a little library that can be reused in arbitrary ways. So Racket tools are mostly not one-shot batch mode executables. And you have this set of APIs for interacting with the machine. But this last point here, all these APIs share a single unified context. I sort of alluded to earlier, but it's really, really, really important because, again, I didn't have to configure anything. There's sort of some shared state that exists somewhere in the machine. And you could sort of ask questions, okay, well, don't we hate shared state? Isn't global state bad? But in this particular case, this really is doing exactly what I want because basically when I launch the Racket executable, it creates a context that has exactly the set of packages in that project in it. And then all these other tools can just sort of assume that those are present. Now, of course, it seems like to some extent we have this as well in Haskell. We have the GHC API. Many tools do use the GHC API, and one of the standard ways for using the GHC API is to spawn a little interpreter environment and to interact with it. And again, the context really is the key difference here. Racket tools don't need to create their own interpreter context. They're designed to be loaded into an interpreter context. If you've ever tried to use the GHC API, it's surprisingly tricky to spawn a little session, especially if you want to get all your packages in scope. And since all those same tools live in the same context, they can actually communicate with each other and they can create their own little derived contextual state. So if you have some library like Scribble that creates these documentation files and things like that, then it also knows, based on other configuration options from things lower in the stack, it can also store its information in some location that's a subdirectory of that. And then again, it abstracts over that stuff and you don't have to have tools that worry about where specific files go. That stuff is just encapsulated by the API. And really, this is just a form of inversion of control, right? Instead of having each individual tool create its own little interpreter context, its own session with something like GHC, they get loaded into something where that's already present. And so one way that we can think about that is, most Haskell tools that currently exist effectively have type IO unit. But all the Racket tools have this type. And that's really amazing because that HIC end guy has a lot of wonderful things in it that we want to have access to. But, and it's, surprisingly difficult to create. So we can imagine a parallel universe where things are a little bit different. And Cabal install doesn't just spawn GHC subprocesses. Instead, it actually imports the GHC API and it creates a little context. And then when a build operation is executed, it just calls the appropriate function to start off a build. And then that happens, it modifies this sort of state of the machine, state of the environment, and then you can go on to execute more operations in that same environment. So instead of explicitly having these separate commands, and I mean, you could have them as a convenience operation, certainly, which also Racket does, but they could effectively just be small wrappers around these public API functions. And so then if you have something like Google, then it just provides this context-sensitive generate database operation, and all the stuff is just wonderfully already there because it's provided in that HSCN. So the big elephant in the room here is that in Rackets, these APIs are extremely stable. And this is something that I'm actually very glad has been brought up by a number of different people over the course of today, which is that the GHC API is very, very difficult to use. It's not particularly well defined, and it changes a lot. So Racket has really been architected in this way to be reused, for all these things to be assembled. And GHC has never really committed to doing something like this. So we can sort of imagine a hypothetical alternative where we have everything in a wonderful state, but that would be very hard to do. So I think what would be nicer would be to try to move incrementally in this direction by picking particular tools, maybe starting with HIW', because I think HIW' is relatively close to GHC, and just trying to figure out, is there some way that we can pull out the things that it specifically needs and codify that as like a kernel of the public API, and then slowly expand it by looking at other tools and providing what it needs. But again, the key point here is that you want to have a public API that's explicitly intended to be used by clients. Oh, I was supposed to have a final slide here, which was a really nicely beautiful looking end slide, but it didn't have that much content on it, so it's not the end of the world. So just imagine it looks really good, and that's all I have to say. So any questions?